Hey there, Mustangs. Welcome back to another edition of No Hair, No Problem. Rosenwald here with our notes for Chapter 4B, which is dealing with the graphs of sinusoidal functions. So what exactly is a sinusoidal function? What the graph is? What does it entail? This is a very big concept in the engineering world. In fact, I've got up here on the background here an example that relates to most of you guys. I'm assuming you guys are familiar with the idea of noise canceling technology and how it exists out there. That we have, these headphones that you could put on and noise is coming in, yet somehow the sound is just not getting to your ear. Why is that? Well, if you look at these pictures here, these graphs actually are related to sinusoidal functions. And what we're doing is we're taking sound, which moves in waves, and we're talking about in physics, you guys are going to do this. You're going to be talking about harmonic motions and frequencies and wave patterns. And so in this case, we're talking about sound wave, which moves in this sinusoidal pattern. Well, how do we get it to actually cancel out the sound that's coming in? What we do is we look at the wave that's taking place, and in order to cancel out that sound wave, we create an ambient sound wave, which is the exact opposite sound that's taking place. So as sound comes in, we get this sound wave going like this. And then in the blue, we get the opposite sound wave, which is the ambient sound. And if you put them together, they net a zero sound, which is the noise cancellation technology. So it's a pretty big concept, as I said, in the world. We're looking at stuff such as earthquakes, where when we have an earthquake taking place, there's this shock that takes place. And what happens is it's really just a wave pattern that's going on back and forth. We have these buildings that exist out there that if they can't handle the shock wave of an earthquake, that wave taking place is going to go ahead and cause the building to just break apart and collapse. So they have these massive, what's called shake tables or shake zones, where the ground actually shakes intentionally. Engineers will build on top of this, and what they're trying to do is actually dampen the wave. And so what happens is you get the shock that's going up and down real fast like this. Well, what they do is they try to counter it by having the ground actually move in the opposite direction of the wave that's taking place. So if it's going up, the wave will actually counter it to take and actually dampen the shock wave, which essentially gets rid of all of the bounce that's taken place. So imagine it like struts and shocks that are on your car. They're trying to cancel out that bouncing that's taking place. Okay? Real big concept, but it's actually pretty easy. What we're going to do is we're going to go ahead and get started here, and I'm going to go kind of quickly through this stuff. But again, if it's any point you're stuck, feel free to go ahead and just kind of pause the video. Go back and watch what you need, but I'm very confident you guys can get this one. It's a pretty easy concept, okay? So let's start off first with what the sine graph actually does look like and where it actually kind of comes from, okay? And what we're going to be talking about are the transformations of graphs. This is the graph of an actual sine wave and the way it's actually appears. And so if I was to go ahead and put a cosine graph on here, y equals the cosine of x, you can see that this is very similar. I'm going to move this to the top. I'm going to actually save it here because I meant to have that up there and I forgot. All right, but this is a sine wave and this is a cosine wave. Now you can see that these are two almost exactly identical waves, but what you should notice here is that these two waves are offset from each other by approximately pi over 2. Okay? Everything we do in this section is going to be relating to 5 points that actually make up our curves. And we're going to be taking those curves and moving them side to side, up and down, and all that stuff. This right here, between the green and the red graphs, this is the cosine graph, this is the sine graph right here. They are offset by pi over 2. This is one of our identities that's going to come into play in chapter 5, so I want you guys to just see it. But let's turn off cosine here. Let's just talk about the sine graph and actually what's happening, okay? So what we're going to be talking about are the 4 main transformations that could take place in our graph because of changes that happen to our functions. Now, this is nothing new. We actually did this back in chapter 1 when we talked about function transformations, okay? So the first transformation I want to talk about is when we take and we add a c value. A c value, if you remember, takes our graph and moves it side to side. So this is what the graph is going to look like. You can see the graph is just moving side to side, but the 5 points that are there are the 5 points that are going to stay in place. You can see from the original graph that we've taken every one of the points in this case and we shift them over to the right, and we take these and shift them to the right, and everything shifts all to the right. So we're going to talk about later how this is called a phase shift, okay? The next transformation that we're going to talk about is an up and down shift that takes place. So you can see right here the graph itself is moving up and down. Okay. This is a vertical stretch or a shrink vertical, not stretch or shrink, just a vertical shift taking place. So as I add 1 or 2 to it, you can see the graph goes up, and then all the points go down, and we can see the change, the graph doesn't change. All of these movements are called rigid movements, meaning the change of the shape. The shape doesn't actually change shape. It just moves as one solid piece. The two non-rigid transformations that take place, meaning not rigid, it actually is going to change the overall shape, is when we have an A value and we have a B value. Okay? The A value, let's look at this one first. This is what happens when we animate the A. Okay? We can see that this causes a vertical transformation to take place. This right here is called a vertical stretch. And then if the value goes lower and gets smaller, this is called a vertical shrink. Now in this section, we're going to talk about how this is called amplitude, and how we actually can take the sound or the wave and actually make it smaller or bigger. Okay? Let's talk about the B value. The B value is called the horizontal stretch or shrink. And what we're doing is we're ultimately changing the period or the frequency. Okay? So think of it like this. As race car is taking place, I'll give you an example. There's this thing called Doppler shift. And when we have Doppler shift taking place, we have waves getting compressed. And then as things are coming towards us, the wave gets compressed. And as waves move away from us, they get stretched. So I'll give you an example here. Ready? So imagine a race car coming towards you. You hear... and the wave gets pulled and it becomes longer. Okay, so we get a shrink or a stretch taking place. When there's a shrink taking place, what I want you to notice is this right here. Okay, when I look at the fact that I have a 2 right here, normally everybody says that this is a horizontal stretch by 2. And what happened is you can see, well, hopefully you can see that if you look at this entire wave, it goes through an entire wave in pi. Versus earlier, when you look at this dotted one, it used to take an entire 2 pi to get through a whole period. And so this shrunk by half. Okay. When I put in a 1/2 in here, I want you to notice what happens. That normally, when we look at this, this is going to take 2 pi to go through a whole wave. But now it takes, if you look at this, double it. It takes 4 pi to go through the entire wave. So now it takes twice as long to go through the wave as it did before. And that is, if you look at this, 1/2 here, that's when we have a reciprocal effect taking place. So let's jump into this. What we're going to be doing is we're going to be basically just taking and graphing 5 points. Now you can notice that every single time we look at this graph, it's exactly the same. It's a sine curve. In fact, if I actually zoom out on this, you can see this goes forever to the right and left. Okay? And then when I look at how high and low it goes, it always has, when we look at this, a max of 1 and a minimum of -1. So the domain for this is -infinity to infinity. The range is +1 to -1. We're going to focus in on, instead of an entire graph, we're just going to do a box, and we're going to focus on this little section right here that generates the whole graph, just repeated. Okay? So let's derive this and let's go. All right, so jumping into our notes here. Let's get the graph first and how we actually derive this, okay? So our entire graph is actually, we can derive this from our unit circle. That when we look at our unit circle, let's look at these quadrantal values. At 0, we know the coordinate is 1, 0. At pi over 2, it's 0, 1. At pi, it's -1, 0. And then at 3 pi over 2, it's at -1. So when sine is 0, we look at the y value over here, and we can see that the y value is 0. So it's going to be a 0 when when we do the sine of 0. When we do the sine of pi over 2, we're looking at the y value here. The y value over here is at 1. And when we're looking at pi, it's going to be at 0. And then we look at 3 pi over 2, it's going to be at -1. And then at 2 pi, it's going to be back at 0. So there's all of our values. Now, believe it or not, these are actually coordinates. And we call these coordinates critical points. They're the 5 main points that are going to make up our entire picture. So this first one is going to be at 0, 0. The next one will be right here at pi over 2, 1. The next one is going to be at pi 0. Then 3 pi over 2, -1. And then 2 pi 0. So these are our critical points that make up our graph. 0, 0, pi over 2, 1, pi 0, 3 pi over 2, -1, and 2 pi 0. Our goal is to come up with 5 coordinates And these coordinates are going to be derived from the different transformations that are going to take place. Okay? All right, so let's continue from here. So let's plot these points. So this is what the graph is going to look like. And all I did was I took these points and I put them across the top of my graph. There's too much to put into one little space, so I always put the x values across the top, and then I put the negative on the other side. And we have 0, pi over 2, pi, 3 pi over 2, 2 pi. It's at 0, 0, pi over 2, 1, pi, 0, 3 pi over 2, negative 1, and then 2 pi, 0. And then as we do the wave, you can see it continues on in both directions. Now again, we don't need this whole thing. So what we're going to do is we're just going to focus on one section over here. And we're going to keep doing that. Okay? So that is the parent function of a sine graph. Let's look at a cosine graph. For a cosine graph, remember to derive these values. We're going to go ahead and look at all of the x values. So when we're looking at 0, the x value there is equal to 1. When we're looking at pi over 2, the x value there is 0. When we're looking at pi, the x value there is at negative 1. And then 3 pi over 2, the x value is 0, and cosine of 2 pi over 2 is equal back to 1 again. And so the critical points for this are going to be 0, 1, pi over 2, 0, pi negative 1, 3 pi 0, and then 2 pi 1. Let's make this graph, and this is what our graph looks like. Now you can see they're very similar, but the difference here is that cosine starts at 1 versus sine, which starts at the 0, but they're very similar here. Okay. All right, so using these graphs now, let's go ahead and start graphing these and talk about all the different transformations that take place. Okay. First thing, let's talk about a vertical translation. A vertical translation is when the graph just moves up or down. Probably the easiest one we could do. So when we say plus d, the graph is going to move up d. When we say minus d, the graph is going to move down d. Okay. So if we look at this first one here, what's happening is we should see that there's a minus 2 on the outside, which tells me that my d value in this is negative 2. And that means that my graph is going to move down 2. Now what happens with this? Well, what that tells us is that all of these points right here on my graph are going to just shift down 2 because the whole graph has to move down 2, right? And so what that means is that we're going to have new y values here. This value right here is going to be at negative 1 because I moved it down 2. This is going to be at negative 2. This is going to be here at negative 3 because I moved everything down 2. Now, I've not changed my graph at all to the left or right at all, so I'm still going to be at 0, pi over 2 pi, 3 pi over 2, and 2 pi. But then what's the graph going to look like? Well, since it's a sine curve, we're just going to have points here, 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 and here, right? Because this is going to be the same graph every single time. And then we go ahead and connect it, and this is our graph. Now, do the best you can and not make it look like a V. I kind of did a poor job right here. But remember, these are supposed to be rounded, that they're curved, curved, and you get the idea. So now what are the 5 critical points that make this up? The first one is right here, and is at negative 2, 0. Okay. The next one is going to be right here, and that's going to be at pi over 2, negative 1. And then the next one will be over here at pi, back at negative 2. And then it's going to be at 3 pi, negative 3. 3 pi over 2, negative 3. And then we're going to be back at 2 pi, negative 2. So those are your 5 critical points. That's it. That's all we're doing. Just coming up with the graph and the points. All right, let's look at cosine. This one, the graph has got a 2.5 on it, which means my graph goes up 2.5. So what this means is that each one of these points is going to be shifted up by 2.5 because the whole graph is going to move up 2.5. So that means we're going to be at 3.5, 2.5, and 1.5. It didn't move it side to side at all, so we're still here. My critical points, we can start now putting them together, but I'm going to go ahead and make the graph first. So it's going to be here, 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 here. Wait, nope, it's a cosine graph, sorry. Cosine, if you look at it, remember, is going to start up here, go down, down, and then back up. And so what we end up with the cosine curve is we get this like U shape almost. Not a V, it's a U. That's your cosine curve. Put the 5 critical points together. We're going to have our first point be at 0, 3.5, then pi over 2, 2.5, and then pi 1.5, and then 3 pi over 2, 2.5, and then 2 pi 3.5. Okay, those are the 5 critical points. All right, let's move on to the next one, amplitude. So amplitude, think about what the word amp means, or amplify. If you've ever had a guitar, you connect it up to an amp, and what that's doing is we're taking the sound and we're making it bigger or smaller. And that's exactly what we're doing. We're taking and we're creating an A value in the problem. Now, an A value is what's going to cause my sound wave to stretch out or to shrink, to either amplify or, I don't know, de-amplify? I don't know what the word would be there. And then we'll just say shrink. So it's either a stretch or a shrink. Now, I say absolute value because it's important to remember that if I ever have a negative in this, remember that negatives cause reflections to take place. But I need to know if there's a stretch or a shrink taking place. The negative is just its own separate entity. Okay. So if we look at this one, we have y is equal to 1/3 sine of x. The A value here is there's an A value in front of this, which means that it's 1/3. 1/3 in front of it. Watch this in action, how this actually changes my shape. Give me a second to open this. Okay. I'm going to take my shape and I'm going to go ahead and change my A value to 1/3. So about 0.333, right? And look at what happened here. You can see that the graph is now from 1, it is now down here. It is 1/3 what the y value used to be, which means that this is a vertical shrink by 1/3. Okay? And so it's a vertical shrink by 1/3. So what that tells us now is that each one of these values right here has to be 1/3 of what it used to be. Good thing is that for us, 1/3 of 0 doesn't change it. It's not going to move my graph at all, so it still is just 0. But what's going to happen is my top of this is going to be, my top of this is going to be 1/3 away from where it used to be, and 1/3 away from where it used to be down here. So this new value up here is 1/3, and the new value down here is negative 1/3. And this right here, these values are called your amplitude. Okay. Didn't move side to side at all, so it still is exactly where it was before. And as far as the graph, it's a sine curve, so it still has all these values where it normally does. And we're going to go ahead and connect those up. Go ahead now and grab those 5 critical points. And you've got all that you need for this picture. Okay? Let's go on to the next one here. Let's look at the A value. The A value in this is a -2. And so what this tells us is that let's look at it. Okay, let's change this A value to a -2 now. And let's watch what happens here. Okay, this is the picture here, so we can kind of see it. The graph used to be right here, but now it's all the way down here. Well, what happened? By me putting a negative in there, just as I said before, negatives cause reflections. And what we're saying is, by putting a negative in front of the function, we're saying take the opposite y value, which is a vertical reflection over the x-axis. And then that 2 says we're going to take that y value and we're going to stretch it out by 2. Instead of the y value being up here at 1, it would have gone to 2, but then it's going to reflect over to the other side. Okay? So let's go ahead and do this. It's a vertical stretch by 2. And let's talk about each of these parts. The 2f of x is a vertical stretch by 2. And the negative on there is a reflection over x. Okay? So let's go ahead and make the changes. My graph doesn't go side to side at all. We didn't change anything there. But the stretches and shrinks right here, these are going to get stretched by 2. So it's going to be a 2 and -2. Your graph normally is going to be here, 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 and here. That's where your graph normally is, right, for sine. But what's going to happen is we're going to grab each one of the points and we're going to reflect it over the x-axis. So if I took this one and reflected it, it's on the x-axis. It's not going to move, so it stays exactly where it was, right here. But this next one, if I grab this one and I move it, grab this and move it, it's going to go ahead and get moved and be down here, here instead. If I grab this one and move it, it's not going to move. But if I grab this one and I reflect it over, it's going to move and it's going to be over on the other side. And then this next one here will not move. Oh my gosh. okay? And it stays exactly where it is. So now my graph is actually going to look like this instead. It's been flipped over itself, okay? Let's go ahead and grab each one of those critical points. We're going to be at 0, 0, pi over 2, negative 2, pi 0, 3 pi over 2, 2, and 2 pi 0. All right, let's go on to the next one, which is horizontal stretches and shrinks. Amplitude's easy. Up and down is easy. Let's start doing things that actually get a little bit more challenging here, okay? Horizontal stretches and shrinks. So first thing we need to know is the definition that talks about the period. And the period is the time it takes to go through one complete wave. That means from the beginning of the wave to the end of the wave. So if I go ahead and I turn this, let me get this back to even here, so it's back to 1. Okay. The period when we look at this, as I said, is where it starts. It goes all the way through this wave and it stops right here. This is called the period. A time it takes to go from beginning all the way through back to the exact starting point again. Okay. And so in this case, it's 2 pi. Well, what we're going to do is we're going to start taking this and we're going to move it in and out. So remember what happens with this is we take this and if I was to animate this, you could see that my graph shrinks and it stretches and it shrinks and stretches, and we're going to start manipulating this to get some new points. Now, before we do this, it's important that you guys understand something. Okay, let me get this back to reset, so it's back to 0. And let's get this back to 1. Here's one of the things I want you guys to notice. So there's 5 points that are taking place here, right? When I look at the 5 points, there's 1, 2, 3, 4 spaces in between these, right? You can see there's a space right here, there's a space right here, there's a space right here, and there's a space right here. And all 4 of these spaces are exactly equal to each other. You're going to hear me mention a thing called interval, and that's the distance that's in between each one of these spaces. Okay, so let's look at what this looks like. The period for all of these is 2 pi divided by b. All right. Now, what ends up happening is this is where we get that reciprocal effect, and that's because we have a fraction going on here where I have 2 pi divided by b. So let's look at an example right here. If I have the sine of x over 2, this is the same as saying the sine of 1/2 x, right? So my b value in this is 1/2. If I use the formula for the period, which is 2 pi divided by b, that means we have 2 pi divided by 1/2. Now, if we think about fractions, 2 pi divided by 1/2 is like saying 2 pi divided by 1/2. Go back to 5th grade math when you first learn how to work with these. You do the keep, change, flip. If I do keep, change, flip, this is going to become 2 pi times the reciprocal of 1 over 2 is just 2. That means it's now 4 pi. So it used to take 2 pi to get through it, but now because I did the division by 1/2, it gets that reciprocal effect. It actually ends up leading to 4 pi for the whole period. So that means it's going to now take me 4 pi to get through an entire wave. And look at what we're going to do here. We're going to take this 4 pi and we're going to create intervals for what it's going to take place. Okay? An interval is how much space is going to be between each and every single one of my values as I move along this. So take this 4 pi and let's break this into 4 equal parts. And we're going to go by pi for each one of the incremental values. Okay, so what does this look like? Well, if I was to go ahead and start here at 0, because my graph is not shifted left or right at all, what's going to happen is I'm going to go in increments of pi to get all 5 of my values across here. So if I increase by pi as I move along, my next value is going to be pi here. And then I go another pi, I'm going to be at 2 pi. I go another pi, and I'm going to be at 3 pi. And then I go another pi, I'm going to be at 4 pi. And what happened is I am going from 0 to 4 pi. The whole period is going to be from 0 to 4 pi, which is 4 pi long. That's my period. And then and I haven't moved it up and down at all. So my graph for this is just going to be, here, it's a sine wave, so it's just going to be these normal spots. And the graph goes up and down, and there's your 5 critical points. Okay, 0, 0, pi 1, 2 pi 0, 3 pi negative 1, 4 pi 0. And let's confirm this. Ready? I'm going to go ahead and change my b value here to be at 0.5, because that's 1/2. And let's look at what happens to our graph here. we can see all of those values in my graph here. We see that we have 0, 0, pi 1, 2 pi 0, 3 pi negative 1, and then 4 pi. And this is what our graph looks like. It now takes twice as long to get through the whole wave, 4 pi, which is 12.58. Okay? All right, let's go on and try another one. This one's going to be a little tougher because this has 3 transformations taking place in this, okay? The b value in this is negative 2. Okay, now let's talk about the transformations we should see. We have 3 times f of x, which means that we're going to have a vertical stretch by 3. We have f of negative x, which means that the graph is going to take the opposite x value, which is going to take my graph and reflect it over the y-axis. We have f of 2x, which means the 2x is going to cause a horizontal shrink by 1/2. Okay. If we look at the period for this, it's going to be 2 pi divided by the absolute value of negative 2. Okay, so we're going to take the absolute value of negative 2, and that's going to go in here, which is 2 pi divided by 2. And that means we're going to end up with pi. So that means the entire period for this is going to be pi long. It should only be 3.14. So instead of being 2 pi, now it's only going to be pi. It shrunk by half. Take that pi, let's break it into 4 increments, and it's going to be pi over 4 for each one of our increments. Okay? Let's put it all together. You ready? So if I start at 0 here, and I go up by 1 pi over 4 over and over and over. I go 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. Simplify these values. That 2 pi over 4 is 1/2, and that 4 pi over 4 is pi. I'm going to go ahead and do the other side too. Now, why do I do that? We'll get there in 1 second. Okay? So that takes care of the period. Let's talk about the vertical stretch that takes place. Normally, our graph is going to be at 0, 1, and negative 1, but because of the vertical stretch, it's at 0, 3, and negative 3. Okay? Now let's take care of our transformation of the reflection. You ready? It's a sine curve, so normally my sine is going to be here, 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 and here. Right? But what we're going to do now is we're going to take each one of these points and we're going to do what we said, the reflection over the y, taking the opposite x value. So if I reflect this first one here, it won't move. If I reflect this one right here, it's going to move over here. If I move this one, it's going to reflect over and be back here. If I take this one and reflect it, it's going to be over here. And if I take this and reflect it, it's going to be over here. And you can see we still get our usual graph here. Now when we do this, we don't want to fall into what's called the mustache trap. Okay, we don't want to draw a mustache that ends up looking like this when we're making this graph, okay? The continuation for this is that the graph would actually then continue and look like this, just like our normal wave, okay? Now what I want you guys to notice here is that this graph right here looks exactly the same as if I just reflected it over the the x-axis. This is one of our identities that we're going to talk about when we get to chapter 5, okay? Now let's confirm this. Let's look at our picture here and watch the transformation. We said 3, okay. So I'm going to go ahead and put a negative in, and I want you guys to see what this looks like on the picture and how this changes. I have a negative b going on here, so watch what happens here. If I take this graph and I go negative b, so I'm just going to put it right here. I'll put it at negative 1. You can see what happens is the point that was on the graph that was over here originally now has been reflected and is over here. Okay? And if I continue to change this, I think it was a negative 2. I don't know, whatever. You get the idea. You can see that this is the new graph and the entire stuff. All of the values that we had over on the right have now been reflected over to the other side. Okay? All right, and the 5 critical points, I did not write those, but you get the idea. All right, let's move on to another one here. This one is going to be the transformations. We're going to look at this. And again, I would recommend trying to maybe pause this at some point and try some of these on your own. But let's look at each part. We have a 1/2 here in the front, and we have a 1/3 right here. So my b value in this is 1/3. The transformations here, we have 1/2 f of x, which means that we have an a value of 1/2. This is my a, which means we have a vertical shrink by 1/2. And then we have a 1/3 on the inside, which means I have a horizontal stretch by 3. Why do we have a stretch? Well, if I take the period, which is 2 pi over 1/3, and simplify it, it's going to now equal 6 pi. So instead of equaling 2 pi, now it equals 6 pi. Break this into 4 increments. 6 pi divided by 4 means that each movement is going to be 3 pi over 2. So I start at 0, I go up by 3 pi over 2, keep doing that until I get to 6 pi at the end there. And from 0 right here to 6 pi, it is 6 pi long, which is our period. Okay? Normally my graph would go up to 1/3, up to 1 and down to 1. And what happens is in this one, we have our vertical shrink by 1/2. So we're going to go up to 1/2 and down to negative 1/2. And then we'll go ahead and make our graph like usual. So we got point, 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 point. It's a sine curve, right? Oh, sorry, it's a cosine curve. Cosine curve, it goes here, 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 here. And we'll go ahead and connect all those and we get our cosine curve. 5 critical points from this. All right, 0, 1/2, 3 pi over 2, 0, 3 pi negative 1/2, 9 pi over 2, 0, and then 6 pi 1/2. All right, so now we're at the point where you're going to need a calculator because these get a little bit more tricky, okay? These are phase shifts, and what we're doing is we're moving the wave to different positions, okay? We're changing the phase of it. And so what happens is all we're doing is we're taking and we're moving the graph left or right, okay? So when I look at letter B here, that minus pi means that we're taking the graph and we're moving the pi value that C value is pi, so we're moving it right pi. Now what happens with my graph? Well, the period doesn't change because there's no B value here aside from 1, so the period doesn't change and the interval doesn't change. Normally, my graph would start right here at 0. This is the typical starting point, right? But what's going to happen is we're moving to the right pi. Now I'm going to go ahead and reset this so we can kind of talk about this here and you can see it. Okay? But if I go ahead and take a C value and I shift it to the right pi, I'm essentially moving it about 3.14. I'm going to move it 3.1 so we can see it. I'm going to take my graph and I'm going to move it 3.14, or in this case just 3.1. Okay? And what we can see is that the entire graph is still intact exactly as it was, but what happened was all of my points, this point shifted over, this point shifted over, every one of my points shifted over. The whole graph shifted by pi, which is 3.14. So my graph no longer starts at 0. My graph now is going to actually shift to the right, and now it's going to be at 3.14 or pi to the right. Okay? And then from here, we're going to go in increments of pi over 2. So if I start at pi and I go up by just pi over 2, we're going to be at 3 pi over 2. And I go up another pi over 2. I'm going to be at 4 pi over 2, which is 2 pi. And then I'll be at 5 pi over 2. And then I'm going to be at 6 pi over 2, which is just 3 pi. And you look at the period here, you can see from 3 pi to pi, 3 pi minus pi is still equal to 2 pi, right? So my period is still 2 pi long, but it's just all been shifted to the right by pi. Haven't changed the up and down direction at all. It's a sine curve, so we're done with the graph. We just got to go ahead and put the points in here. And there's our 5 critical points. Okay? Let's talk about another one here, but this one we're going to go ahead and make a little bit more difficult. Okay? Pi was an easy number to work with. Pi over 6 is not an easy number to work with. So when we look at this, I am moving, my C value is negative pi over 6. It's always the opposite, which means my graph normally starts at 0, but now it's going to be shifted to the left pi over 6. There's no vertical stretches or shrinks to this, so I'm still at 1, 0, and negative 1. Now, what we're going to do is my period has not changed. There's no B value here to change this. So it's still 2 pi over 1, which means it's still 2 pi. If I do the interval for this, it's going to be 2 pi divided by 4, which is pi over 2. So we have to start at negative 1/6, and we're going to have to add 1/2 to this. Now, this is a pi, obviously, in a pi. So using negative 1/6 plus 1/2, this is where calculator is going to probably help you. If I add 1/2 to this, which is 1 pi over 2, I'm going to be at pi over 3. I'm going to add another 1/2 to this. I'll be at 5 pi over 6. I add another 1/2 to this. I'm going to be at 4 pi over 3. I add another 1/2 to this. I'm going to be at 11 pi over 6. That's the graph. Now we'll go ahead and plot the points. Or that's all the points. Let's go ahead and graph these. I'm going to point here, 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 here. Go ahead and graph it. And then your 5 critical points. That is it, my friends. Next time when we do this, what we're going to do is we're going to start trying to create problems where we have all 5 of the transformations put together in one problem. I say 5 because I'm adding in reflections here. So such as an example like this, we'll talk about how to navigate this at a later time. But hopefully you guys got it. Your homework is on Schoology. It's just a worksheet kind of practicing this stuff, okay? If you have any questions, reach out to me. I'm available during 1st, 3rd, and 7th. But until then, you guys take care, be safe, and have a good one.